talk is about phenomenon algebras or q-Araki-Woods phenomenon algebras, and they are some q-deformed counterpart of the classical CAR phenomenon algebra that was introduced by Araki and Woods. Yeah, so this is not in the same spirit of this conference, but I hope that you find it. So we actually talk about whether such phenomenon algebras are factors, meaning that their centers are trivial or not. And these phenomenon algebras are associated with three data. We start with a real Hilbert space, number between -1 and 1. So unlike many examples of quantum groups where you have only positive or non-negative numbers, here we allow negative numbers as well. And you have a representation, orthogonal representation of reals on this real Hilbert space. And I plan to give construction of these algebras and discuss some of the history that what people have tried about proving their factoriality, and in the end I will tell about our contribution in this session. So these are so I'll start with the case when q is 0 and q is 0. So the simple case where we just have one datum, like a real Hilbert space. So HR is a real Hilbert space, and we will work in separable settings. And we complexify the Hilbert space, and we consider these free Fock spaces, which are nothing but just direct sum of n tensors of Hilbert space. And H naught will be complex plane, and omega will be a fixed distinguished vector, unit vector, which we call vector. On these Fock spaces, we define something called left creation operators. For each fixed vector C in H, you send omega to C and an n tensor like this to n plus 1 tensor like this. So you attach C in the beginning in the left side. Similarly, one can define the right creation operators where you attach in the right side. And one can show that they extend to bounded linear maps on the whole Fock space. And then we define free Gaussian phenomenon algebras. They are subalgebras of bounded operators on the Fock space. They are generated by the left creation operator and plus the left inhalation operator, which is the adjoint of that creation operator. And these phenomenon algebras were, I think, introduced by Michaelescu in the setting of his study of free probability theory. And some of the properties, like the vacuum vector, if we consider this vector state, so they give rise to a tracial normal factorization on this Gaussian phenomenon. And one can show that when I think dimension greater than 14 is not required. But yeah, in this case, one can show that the Gaussian phenomenon algebras are actually isomorphic to the group phenomenon algebras of free group factors. And once we know this isomorphism, then you can immediately deduce that they are common factors, and they are at the same time full factor, in particular non-negative factors. Okay. Now we fix an orthonormal set in this Hilbert space and denote Li by these creation operators. Then we have such kind of relation. So 0 is put here just to say that we want to actually consider a Q version of such relations. So we want to get a Q deformation of commutation relation like this. So if you have Q equal to -1, then you get CR relations, but we actually don't consider Q equal to -1. So For that, for such operators are also represented on certain Fock spaces. But we now have to consider some information of that. For that, so now we have two data. Like we started with, we want to construct a phone algebra with three data: Q, H, R, and orthogonal representation. But for now, we still keep the representation to be trivial. So we have two data: Q, a real number 1, and a real Hilbert space HR. And on these n tensors, we define deformations of the inner product, which are just summation of spaces like this, where these in are just inversions, number of inversions for the computation is in the symmetrical. And then we complete this. H naught will again be just the complex numbers, and H0 will be the Hilbert space that we started with. And we take direct sums of these completed Hilbert spaces, and then we call them q-Fock spaces. And on such spaces, we again define creation operator, but now the definition of the creation operator is same, but its adjoint actually will look different because we have a different inner product. So they again send omega to C and a left. And Bojenko and Spiker showed that who introduced such operators, they showed that they actually extend to more than linear operators on the whole of q-Fock space. And in the same spirit as before, one can define the q-Gaussian for Neumann algebras the same way, but now they are acting on the q-uniform Fock space, and they are generated by the creation plus the annihilation operators. And they satisfy some similar properties, like when the case when q were 0. So here also the omega, the vacuum vector omega induces a normal faithful Tracy state. And unlike the case when q equal to 0, proving factoriality of such algebras were not so immediate, and it were work of many people. So, for example, these three authors showed that there are factors when dimension is infinite, and then some other result of regarding the end prove that in general that they are factors, and they are also non-injective in the sense that well, one formulation that they can't be approximated by 5-dimensional. Okay, so we now consider a different deformation where we have q equal to 0 now, but the representation will be non-trivial. So we still have only two data, but we are taking q equal to 0. So we start with a real Hilbert space, and AUT is one parameter strongly continuous group of orthogonal operators. We again complexify the Hilbert space, and these UT naturally extend to operators. Now we use Stone's theorem to get such unbounded operator in general. And using these unbounded operators, we define a new inner product on the complex Hilbert space, like this. Where at first it may sound and look quite weird, but this, and they actually give an inner product simply because they are invertible operator, and HU denotes the completion of H with respect to this new inner product. And it's not at first clear, but HR actually the real Hilbert space that we started with, they isometrically sits inside HU. So in the sense that when you restrict this, well, when you have the same C and C coming from HR, then you get back to your original inner product that you started. Okay. Now we consider polynomial algebras generated by creation and annihilation operators. So as earlier you consider this free Fock space. So here we are still in free Fock space. We are not considering Q deformation, and you consider creation and creation operators as we had seen earlier. And it's so Selektenko introduced these phenomenal algebras. They are called q-Araki-Woods phenomenal algebras, and they are in the same way defined to be the phenomenal subalgebra of border operators and the Fock spaces. And here again we vary C only from the real Hilbert space. But now, so as in the case of Gaussian phenomenal algebras, these vacuum vectors will remain cyclic and separating. But the normal faithful state that we get is no mutation. So now we are in the setting of type 3 phenomenal algebra, as soon as UT is not true. And he also showed that this is a factor, and its type is 3. I'm not going to talk about its classification here, but they are a factor of type 3 when UT is non-trivial, and they are non-injective. So now we want to combine this construction of Selektenko and the Q deformations of Bujaykian spiral. So now we have 3 data. So we have a number between -1 and 1, a real Hilbert space, and orthogonal representation of real form Hilbert space. And we had, so this HU is the deformation due to which comes from the analytic generator of UT on the complexification. And we now consider Q Fock space of this Hilbert space. And the same way we define liaison operators, which sends vacuum vector to C. I have just repeated it here. And the definition as before is the same. The q-Araki-Woods phenomenal algebras are generated by the sum of creation and annihilation. But now things are acting on q-deformed Fock spaces of this deformed Hilbert space. And as we saw in the algebra of Selektenko, this also induces a normal faithful state, but now we again have a non-traceable state the moment UT is not true. So we, unlike the case when Q equal to 0, proving that such phenomenal algebras are factors were not so easy. Although the definition came in 2003, it took quite some time to prove that they are factors. So here is some history as what people have tried. So Hive, who introduced this phenomenal algebras, he proved that when the representation is weakly mixing, meaning that there is no eigenvector or eigenvalue of operators, then they are actually factors and they are non-injective. A result of Nelson from 15 says that when this parameter is close to 0, then we have this isomorphism. And we know that these are factors. So in particular, they are factors. And so these are, so when UT is almost periodic, this is a result of EI, but there was some gap in info. So when UT is almost periodic in the sense that the Hilbert space is generated by eigenvectors. So this is completely opposite to what is here. And when the dimension is infinite, then they are factors. Two independent papers in 17 actually assume that when UT has a non-zero fixed vector, meaning that one is the eigenvalue of these UTs, then they are factors. And a very recent paper of 4 authors proved the factoriality in almost all cases when dimension is at least 3 or when dimension is 2, but Q is large in certain sense, then they are factors. So the only remaining case where when dimension is 2 and Q is small in a sense. And that's what we completed. So our method actually works for any finite dimensional Hilbert spaces. So we showed that these q-Araki-Woods phenomenal factors, and they are moreover of type 3 that we expect the moment ut is non-trivial. And the proof also says that these factors are non-trivial. So I want to discuss a bit about our approach in how we proceed. And our approach actually are quite different than what previous results had, previous papers had considered. So they usually consider some kind of subalgebras which satisfy certain mixing property, but we actually take a very different approach that was recently considered by some other people when it is trivial, and we actually generalized here what was and not trivial. So this approach is via conjugate variables. So we have these three data. We fix an orthonormal basis for this Hilbert space. We take, so the orthonormal basis is chosen in a certain way so that the corresponding operators that we are considering these AIs, they are kind of eigen operators of the modular operators in the standard form that we consider. So AIs are these operators which are some left creation and left inhalation operators, and these are the operators which generate the whole von Neumann algebra. So we consider just the star subalgebra of this generated with this, and then we define something called quasi-free difference quotient. So these MQs are just the shorthand notation for this algebras, and these tensor products, one can think that they are actually, they have left multiplication and right multiplication, so they are bimodules over MQ. So in particular, they are bimodules over these star algebras. So the moment they are bimodule, one can consider the unique derivation from this algebra to this algebra of opposite von Neumann algebra, and we define the unique derivation in such a way that it satisfies this definition, and you extend them recursively over the products of these things. So once we have such derivation, we define something called conjugate variables. So via standard form, due to the cycling and separating vector coming from this vacuum vector, you can think these algebras to be sitting inside L2 of L2 of. So these operators can be thought as unbounded, densely defined unbounded operators on L2 of L2. So in that sense, the conjugate variable is defined to be a vector here in the GNS construction, where these are just vector state of vacuum vector, and this satisfies this inner product relations. So in general, we don't know whether conjugate variables exist, and the conjugate variable exists if and only if one can see that this one tensor one actually belongs to the domain of the adjoint of the class. And we actually want to prove that conjugate variables exist for these operators. And one can define such conjugate variables and quasi-free different quotients even for general von Neumann algebra, as long as it is generated by, say, so why do we want to study such conjugate variables? This is because of this result of Nelson. So this result is in an abstract setting. It says that suppose you start with a von Neumann algebra which is generated by a finite set, which is self-adjoint in the sense that if A belongs there, then A star also belongs there. And well, they consist of eigenoperators. I won't go into that. But what is more important that these finite set, the operators there, they admit the conjugate variables in the sense that we defined earlier. then you can conclude that they are non-rectified. So we have this abstract result. All we want to prove that they are conjugate variables, and then we are done. So recently Miyagawa and Spiker, they showed that when UT is trivial, then these operators, this AK that we had defined here, yes, these operators actually admit conjugate variables. And so this was when in the tracial case, we extended this result in a non-tracial case. When UT is non-trivial, the representation that we started with, then AK admit conjugate variables for all k. And then we combine this result and this theorem of neutral to conclude that our q-Araki-Woods algebras are factors for Hilbert. So that's all I wanted to say.